Let's start. The first problem is poslaniec, POS, messenger in English. What is happening in this problem? We are given a graph of quite small size and was up to 100, then 500 queries. Each query described by 2 vertices u and v and length d up to 50. We need to say what is the number of paths from u to v of length exactly 50 that they do not visit u or v multiple times, but they can visit other vertices multiple times. And some number that we need to print the answer modulo that number. This is messenger. POS. What will be brute force for this problem? Maybe not brute force, but still some too slow solution. From starting vertex u, after we made some steps already, possibly with repetitions, what is important is in which vertex we are right now. It will be dp of I, the current vertex, and the number of steps already, say steps. And from I we consider every next possible vertex. We go through all the edges going out of I. And the complexity to answer a query will be O of the number of queries, and for each query the number of possible steps is d times, for each I we iterate over neighbors, in total it is m. For each vertex we iterate over neighbors, in total we iterate over all the edges. And this is too slow, we need to do something faster. We want preprocessing. It's quite easy to make a preprocessing that for a pair of vertices it will find the number of paths of, like, we could run this thing for every pair of vertices once, where, like, instead of here d we have max d, just exactly 50, and then we will precompute all the answers for each of n square pairs. We do this whole thing assuming that distance is 50, but also remembering other values in the process. So it will be times the maximum possible d times m. This will be solution with preprocessing, not to repeat any computations, and it is still too slow. This is m is up to n square, so we can also say this is n4 times d. And n was up to 100, so n to 4 would be fine, but d is up to 50, and m is up to n squared. That's too slow, but should allow us to solve some subtask at least, and that is, well, we already know how to do, I think, the second subtask, because in fact we don't have, the second subtask doesn't require preprocessing, so the organizers apparently didn't predict this thing. We could solve version with what, n up to around 50 maybe, and any q. This is what we can solve. Now we want to deal smarter with the fact that we cannot visit vertices, the starting and ending vertex multiple times. This is why one preprocessing is not simply enough, because for every separate query about starting vertex and ending vertex, we allow some paths that maybe visit multiple vertices multiple times, but S and T must be unique. having this value doesn't help us in computing the number of such paths from S to some different t prime. The thing that we can preprocess though is the number of all the paths between S and t, and maybe that will help us in some way. And please put scores in Google Sheet, then I understand which problems are easier, which are harder, so when I should talk more about something and when it's obvious for you anyway. Okay. We can preprocess the number of all the paths from S to T, maybe visiting S and T multiple times. This will be just any of S, T, and the number of steps, say K. K is the number of steps. In one complexity, can I do this? For every starting vertex, maybe there are O of n squared times d states of this dp, and for each of those I iterate over the next vertex after t. So I could say that this is times n, but in fact, yet again, it's the number of possible t and k are d times n, times when we for every s iterate, oh, the other way around, the number of possible pairs k and s is O of n times d, times for every t we iterate over neighbors. In total we iterate over all edges. So this is not n squared, this is just m, which is the same in general for general constraints in this problem, but it's good to be able to well estimate the complexity. So this is the complexity of preprocessing, and it's good enough. Also we can say for general case that it's n cubed times d, which is fast enough for our constraints, n up to 100, d up to 50, because we have around 50 million here. But we need to subtract those paths where we visit S or T multiple times. Can we do it? So this is good. This is any, and also my goal will be to compute good of S, T, and K. Maybe using those values any that I already can compute. How to do it? I will later say a bit about similar problem from AdCoder DP contest that also subtracts those incorrect cases, incorrect things that invalid things that we shouldn't count, and then we have got, the correct answer. So I see in scores in Google Sheet that this problem wasn't very easy, because indeed it isn't trivial how to compute now this array good as preprocessing. For k equal to 1 it is easy, because we need to jump directly from S to T. Now what happens for bigger k? By the way, maybe if your first loop, the outer loop, if your program will be over k, then it will be better for cache to, instead of any stk, to have any of kst. The order of dimensions in DP should be similar to the order of for loops. Then it's faster to iterate first by this dimension, then second one, and then third one. But here we don't care about implementation, we just want some solution in good complexity, not caring about a constant factor. Okay, from S to T we want, let's say, the number of good paths with some k equal to, like, I don't know, 5. And for that, assuming that I already have all smaller values of dp, can I use it in some way? What is a bad path? Bad path from S to T will be such a path that it goes for some time, it visits T or S, and then it still keeps going, maybe visit things for the second time, and eventually finishes in T. So it consists of a good path, so every bad path is of form good path from S to T, good, then just any path to T, or good path or just path from S to S itself. Let's say that it's good. Good means it doesn't visit S or T in the process, and then any to T. So one idea is to maybe iterate over that and to subtract something. The other is to try adding more dimensions to our dp. Maybe we should have something like dp of S, T, current vertex, and K, where S and T are those forbidden vertices, because we started from S, and C is the current vertex in which we are in. This would give us O of S, T, and K, there are n squared times D possibilities for that, and for the current for every C we iterate over other vertex, this would be M. This is not good enough, and it's equivalent to one of our previous solutions, I think. So let's forget about this thing. Instead, we need to do the thing on the left, to subtract incorrect cases. How to do it? If we have already computed array any and array good for smaller k, then I can iterate over, let's say that the length of this first part is I don't know, k1, the second part will be k2, and k1 plus k2 must be equal to k. So we iterate the I want to say that good of stk is equal to any of stk minus something. Minus what? Minus the sum over all k1 from 0 to k of good stk1 times any of t and k minus k1. This will subtract cases where from S we go to T without repetitions before that, and then from T we go just in any way to T. Because every path from S to T that is not good, for sure it will for the first time visit S or T in the mid, somewhere in the middle. We iterate over that moment, k1, and I say, okay, this is the number of good paths so far, times just anything that will happen later. This covers case A, and now case B. Is it trickier or not to compute? Let's think. So the word good here means that it doesn't visit S or T in the process. So we cannot just use good from S to S, because that would just forbid vertex S itself. We need array good from S to T just computed for vertex S. The number of paths from S to itself without visiting T in the process. Can we do that in our solution? Can we have that as maybe the third array or a part of array good? Let's think about it. And if yes, then we will have full solution, because the number of states of good is this thing, there are O of n squared times d states, and each of them we iterate over k1, which is up to d. So this will be a complexity n squared times d squared. And now what remains is case B. Are there any questions at this moment? Do you understand everything except for the part with B that we haven't yet covered? If yes, tell me in the chat. No questions. So from the starting S, I want to count the number of paths like this, maybe with repetitions, that go back to S and they do not visit T. So this will be maybe array, I don't know, good 2 of S T K, where now good 2 means the number of paths from S to itself without visiting S or T before that. So now the second dimension denotes extra forbidden vertex. Can we have that? Well, can we compute good 2 in similar way that we compute the array good? Let's think. The good 2 from S to S itself, it will be any, just like here we had the formula on the right, this one. I want to write the same thing. Here it will be any of S, S, K. So I want to rewrite this as something else, as that thing. Minus the sum over K2, K1, the number of steps till we hit something bad, of good 2 of S, S, K1 times any of S, S, K minus K1 plus this thing plus either we will eventually visit S or we will visit T before that, which is also forbidden. So this would be just good from, oh, here I meant T, because T is forbidden, and from definition this thing, good 2 of STK1, is the number of paths from S to itself, not visiting other, not visiting vertex T at all, and not visiting S in between. Then here the number of paths from S to T without repetitions times any from T to S. We have the sum over K1 of that. And we need the same here. We will here say plus, and we use good 2 because we wanted to cover the case B written on the left. And here we have good 2 of something, where this something represents going from S to itself without visiting S or T in between. So this is just good 2 of SSK1 times anything from S to T, just as is written here. And we have now 3 arrays. I'm not sure, maybe it's possible to do that just with 2 arrays, but each of those arrays has n square times the states, and to compute new value we iterate over k1 times d. The complexity is O of n cube times d, which is around 50 million, and it is the intended solution. Now is the time for questions. I will maybe make sure in the editorial if this was the intended solution. It doesn't look intended at all. Oh, and we need to answer queries, but we do that in constant time, right? We pre-computed the good of STK. Yeah, so our complexity is actually, apparently we got something completely different from the intended solution. The total complexity we have is O of n cubed times d for preprocessing plus q. Each query we answer in constant time. I see that the intended solution has complexity, this is intended, has complexity O of n md plus q times d square. For m that is around n squared, this is the same. If m was smaller, then the intended solution would work and mine wouldn't. Okay, apparently they do not count the whole array good in between. Just when they have a query for vertices s and t, then they compute good of st for every k, and for every k you iterate over smaller values k1. Because if we go here through everything, we will see that our good of st only uses good of ss and like good of st and also good 2 of ss, so also the same thing. And the general preprocessing that we need is only the array any. We need to compute any, we need to go through the whole graph. So any we precompute in time n times m times d, so this one, this is the intended precomputation, and indeed we have this complexity for array any, and good 2 you can compute just for the query. So that's the difference. But q is huge, so you can also do it for every s and t. Actually, there will be only n squared different queries about different pairs s and t. Let's move to the next problem. And this will be pra, diligent, Johnny. It was the one about permutations. Okay. Diligent Johnny pra. We're given some permutation, say 3, 1, 2. I think this was the example one. From this we move to the lexicographically previous permutation, the one that is just before that, when we sort all permutations lexicographically. Then no, it should be 2, 3, 1, then 2, 1, 3, and we continue till we get 1, 2, 3, 4, 5 up to n, the sorted permutation. For every step from one permutation to the next one, we wonder what is the number of possibles, what is the number of required swaps to move between two permutations. Here, between those two, 1 is enough. Between those two, 2 are necessary. For example, we can swap 3 and 1. We would then get 1, 3, 2. Then we need to swap 1 and 2 to get 2, 3, 1. So it isn't even trivial to solve this problem in n factorial times polynomial, because then we would need to move to figure out a way to move to the previous permutation and then compute the number of swaps. We will focus first on this number of swaps. To find the previous permutation in subtask for n up to 8, whatever it was in the problem, we could use next permutation. I don't know if there is a function previous permutation. I'm not aware of that. But I would start with sorted permutation, and I would run next permutation of that. There is a function next permutation in C++, till we get the permutation from the input. But still, for two consecutive permutations, I want to know the number of swaps to get from one to the other. It actually doesn't matter if I move from one to the other or the other to the first one, because it's symmetric. If there is a sequence of swaps that gets from permutation A to B, then if you reverse that sequence of swaps, you will get from B to A. So the optimal number of swaps must be the same. And in general case, there is n up to, I think, 100,000. There is also subtask like that or similar. And there is subtask where the input sequence is sorted decreasingly, which means you need to count the sum of the number of swaps required to move between all the permutations, from the sorted one to decreasingly sorted one, going through all others. Let's figure out what is the number of swaps we require to move between permutation to its predecessor, the previous one. First, let's figure out what is that previous permutation, how we should represent it. When we are looking for something that is next or previous in lexicographical order, to make it close to the initial thing, we need to have long same prefix. For example, if there is some permutation and you want to find the next one, if possible, you should save as long prefix as possible and just swap these two numbers. If that's not possible, maybe this thing you can save and only swap the next thing. And here, if some suffix is sorted, like 257, for sure you cannot for any suffix here figure out a permutation that is smaller lexicographically. Instead, you need to extend. And when eventually you meet a number that is, so the suffix is now 6257, this number is greater than the next one, then this is not permutation that is sorted, and there is something before that lexicographically. The permutation before that is 5, because we should move from 6 to something smaller, and then as big as we can get is just decreasing sequence. 5, 7, 6, 2. And we need to figure out the number of moves required between those two. In the exact values don't matter, it's only their relative values. So we can use coordinate compression to say that this is the same permutation as 3, 1, 2, 4. I saved the order of things by compressed it to 1 to k, and from that we move to what? 2, 4, 3, 1. Generally, we will have here some value x, then increasing sequence 1, 2, and so on, x minus 1, then x plus 1, x plus 2, x plus 3, up to k. And from this we want to get x minus 1, k, k minus 1, and so on, decreasingly, x plus 1, x minus 1 is skipped because it's here, x minus 2, x minus 3, and so on, up to 1. Now, what is the number of swaps we need? To analyze this well, you should treat a permutation, you should treat this as a graph with cycles. If you know that x should go to some position, maybe let's put it in good order. So 1 is on the same position as k, 2 is the same position as k minus 1. X minus 1, will it be the same position as x plus 2? Not necessarily at all. Only if x is around k over 2. So it is possible that, let's say, k is 100 and this is position 17 and this is position 80. Let's remember about that. But for this example, if we say that 3 should get to this position, 2 should get to this one, and then also 1 should get to this position, 4 should get to this one, we will get some cycles. Let's consider one more example here to make it not that trivial. What if it is 3, 1, 2, 4, 5, 6, 7, and it moves to maybe bigger font will be useful. 3, 1, 2, 4, 5, 6, 7. It moves to 2, 7, 6, 5, 4, 3, 1. And let's put edges. 3 needs to go here, so I put an edge like that. Then 6 needs to go there, edge like that, and 2 needs to go here, edge like that. Then 1 to 7, 7 to 1, and 4 and 5, like that. We get a graph that looks like that after rearranging vertices. And generally this is how you can figure out the swaps required for changing one permutation to the other, or maybe sorting permutation with swaps. For every cycle, here for every cycle, if cycle has size k, do we need, how many do we need? I think k minus 1 swaps, because we can swap two elements. Then this first one, a, the arrow, the edge means that a should be in position b. So by swapping a and b, we put a in good position, and then we get cycle that is smaller by 1. This cycle had size 5. Now we have 4. Then again we will swap two things. We will get cycle of size 3, then cycle of size 2, and eventually for cycle of size 2 only one swap is enough, because both things will be in good positions. So you need one step to move to cycle smaller by 1 till you get cycle of size 2. Then one step is enough. And then the number of swaps required is just the sum over size of cycle minus 1. And you can analyze this way what might happen, but also from this an important observation about the greedy thing is nice. It is correct to just move any number to its good position. This way what happens is we take just some number from one of cycles and we put it in good position. This way we decrease one of cycles by 1. In particular, this means that number 3 can be wait a second. 3 can be put there. What do I want to say? 3 should get here. Okay, there is some number. If this is x, then this number is x minus 1. It should get to the first position here. So it is optimal to greedily just make the first step as follows. Put x minus 1 in its correct position. On the left it would be put this number on the first position. X minus 1 put it on the first position. Then what we will get from this sequence on the left is what will happen. We will get 1, 3, 4, 5, 6, 7, and we can notice that this is the reverse of this thing. Thanks to the interpretation with cycles, we know that it's okay to make that first greedy step. It is still, we will get the optimal number of moves, because for any cycle we can swap the two previous elements. One of optimal solutions would also do it eventually. And now what is enough is to reverse the sequence, and you can treat that as cycles, but you can think about it easier. That's just you swap first with last, second with second last, and so on. So what would happen on that long sequence on the left, by the way? You swap this one, x minus 1 with x. Then what you will get from that is x minus 1, what should indeed be here. And then 1, 2, and so on. Instead of after x minus 2 you have x, that was inserted here, then x plus 1, then and so on, up to k. And this is exactly the reverse, except for the first element that is already in good position. The rest is the reverse of what we should have. What means the number of swaps required is something like k by 2, plus minus 1, around k plus 2. Let's figure that out exactly. So to reverse a sequence A, B, C, D, E, we need to swap A with E, B with D. So for 5 we should get score 2. If it's even, A, B, C, D, E, F, then we need to swap those 3. So for 6 we get answer 3, what means to reverse a sequence of size S, we need S over 2 floor operations, because the first S over 2 floor things we swap with those to the right. And in our problem, the first operation is to swap those two elements, which means if we have something like this, 3, then 1, 2, 4, and so on up to S, we have one step to swap 3, to swap x minus 1 with x, plus then this has length s minus 1, and we need that many steps to reverse it, and this whole thing can be also written as s plus 1 over 2 floor. Finally, this analysis allows us for n factorial solution, because we can move between two consecutive permutations. For For them, what we need is just to find the common prefix. Then that suffix will change like we described here. And we need to s plus 1 over 2 swaps for that. Where s is the number of things here, the size of the suffix that changes. If we talk about our first example, the 312 sequence, let's compute the score for it maybe. Here the suffix 3 changes, s is 3, so s plus 1 over 2 is, we need here exactly 2 changes. Then on the second step, s is 2, so s plus 1 over 2, floor, is 1. Then here s is 3, so again we need 2 changes. And here s is 2, so we need 1 change. And I claim the answer for this sequence is 6. Does it match what is there in the sample test? Yes, it works. Now we deserve 15 points. But it will be easy to do second or third subtask, then just slightly harder to solve the fourth one for n up to 1 million. Let me change that. Here it wasn't 10 to 5, it was 10 to 6. Okay, let's solve subtask 3. That is a sequence like 6, 4, not 4, 6, 5, 4, 3, 2, 1. What will happen for this sequence? First, we need to handle this suffix, and let's say that our formula that we computed is g of, I don't know, n is n plus 1 maybe of k, is k plus 1 over 2 floor. This is the number of swaps required to handle suffix of length k. Handle means that from one permutation to the next one, some prefix remains, and what changes is suffix of length k. Here, to move from the first permutation to the one with 1, 2 here, we need g of 2 operations. Then we have 3, 1, 2. To move to 2, 3, 1, we need g of 3. Then we have the similar thing, 2, 1, 3, g of 2. Then 1, 3, 2, 1, 2, 3. This is g of 3, g of 2. And we sorted this way the suffix of some length. And we see here some pattern, that what happens is we sort the suffix of length 2, then we move from 3 to 2, and again we need to sort suffix of length 2, and so on. We will make here 2 transitions from some x to x minus 1. So with the number of steps we need to move from 3 to 1 into to 1 to 3, it should be equal to 2 transitions times g of 3 plus between 3 times we sort the suffix. 3 times here it would be just g of 2, but we'll talk about the general thing in a moment. Does it produce correct answer for our sample test? Oh, never mind, because the sample test is 3, 1, 2. But then what happens in more general case? If we are at 4, then 3, 2, 1. Let's, by f of n, or f of k, is the number of swaps for like the answer for suffix of length k suffix. We already computed f of 3 here, and to compute f of 4, that is, what is the number of swaps required to sort this suffix, to move from this to 1, 2, 3, 4, this is equal to 3 times we will move from 4 to 3, 3 to 2, 2 to 1. So 3 times we need g of 4 plus in between 4 times we need to sort the suffix. It will be 4 times f of 3. And the general formula is f of n is n minus 1 times g of n plus n times f of n minus 1. That's something that allows us to linearly solve third subtask. Let's think for one more minute what happened for general case. We have n, then n minus 1, n minus 2, up to 1. From that we will eventually get to n, 1, 2, up to n minus 1. The total thing required for that is f of n minus 1 from definition. This is the total number of swaps on a path from decreasingly sorted permutation 1 through n minus 1 to 1 through n minus 1, sorted one. Then we from this move to n minus 1 and then decreasing thing n minus 2, n minus 3, up to 1. This is just a single step which requires g of n moves. From this we want to sort this, and the values don't matter, the relative order matters, so we have situation same with this one. Now we have a path of moves, in total requiring f of n minus 1 moves, to get to n minus 1, then sorted thing. From this g of n, to move to the next thing, to change the first element, n minus 1, n minus 3, up to 1, and so on. And to get eventually to 1, 2, and so on up to n, this is the goal. We will n minus, how many times we move from, so we have something here n and we sort suffix n times, and how many times we move from value x to value x minus 1 in the first position, eventually to get 1, n minus 1 times. And this is the source of the formula in bottom right corner here. N minus 1 times we do g of n times we do f of n minus 1, because then we sort the suffix. Let's apply it to permutation that is given in the input. So let's solve subtasks 2 and 3. When we have some permutation, like maybe let's take something bigger, 3, 7, 1, 2, 4, 8, 5, 6. It makes sense to move from the end, and what do? We decrease stuff. Here we do nothing, and from here, from this 8, 5, 6, I want to get to 5, 6, 8. Do I know how many steps I need? This is equivalent to getting from 3, 1, 2 to 1, 2, 3, and I indeed know how to do it, because this is similar to our formula. 2 times I will decrease the first element, so it will be twice g of 3 plus after each thing, I think after each thing I need to sort the suffix. I think it will be 2 times g of 3 plus f of 2. Let's remember that this time we don't need to sort the first suffix. But previously we talked about moving from 3 to 1 to 1 to 3. Then we had one more operation to sort the suffix. This is why in the formula here we have here n, not n minus 1. But this time suffix is already sorted, so we are done. And we got suffix 5, 6, 8. Then we extend by 4, by 2, by 1, and now we have 7. So from 7, 1, 2, 4, 5, 6, 8, I want to get to a sorted thing, which is 1, 2, 4, 5, 6, 7, 8. The number of steps I need is the number of times I will decrease 7. Just like here we compressed 8, 5, 6 into 3, 1, 2. I could do the same thing here, or I could just notice that the number of steps, those times I decrease the number, from 7 it will be decreased to 6, then 5, 4, 2, 1, is just the number of numbers smaller than 7. And I claim that here the total cost needed for this transformation is 5 times g of, what is the length here, 1, 2, 3, 4, 5, 6, 7. The length of this thing is 7. G of L plus sorting the suffix of length L minus 1. And 5 is the number of things smaller than the first element, because this is how many times we move from this element to the next smaller one. Then we need to sort the suffix and to repeat. And then we need to do the same when we append here a 3. I need to, from this, move to the sorted sequence. This will be 2, the number of things smaller than 3, times g of L plus f of L minus 1, where L is 8. What solution do we get from this? For any sequence that is given in the input, we go from right to left. For every position, we already sorted the thing on the right, and we need for this number, let's say that this is I don't know, 9, and here we had initially 3, 15 and 7. We know that we already sorted the suffix, but we need the number of things smaller than 9 in the suffix, which is 2, times g of 4, the length, this is L equal to 4, plus f of L minus 1, which is 3. And this is the number of steps we need at this moment to sort the suffix, to get from 9, 3, 7, 15 to, because we already sorted the shorter suffix, to 3, 7, 9, 15. Yeah, we need for every number find the number of smaller things, let's say that it's C, times g of, if we number things 1, 2 up to n, it will be g of n minus I plus 1, this is the length of suffix, plus f of n minus I. Iterating with I from n to 1. We need to increase the answer by that. And the final thing is how to compute C, the number of numbers smaller than the ith number that are to the right. We can do it linearly to solve the second subtask and get complexity n square, and to get O of n log n for the whole problem, we go from right to left and use a segment tree or something like that. There are values from 1 to n, and we have queries. This new value is added, like turn value 3 on, 7 on, then 15, then 3, and give me the number of things smaller than something. This is just segment tree or binary indexed tree. Plus, the very first thing you need to do is use use this formula to compute f of every n, where g was the thing at the top. G of n is n plus 1 over 2 floor. First you do that linearly, then you go through elements and use this formula on the left, where c is the number of smaller elements. The last problem was about some grid or maze, and I think you will be surprised by how easy this problem is. We're given a drawing like the one on the left, and we need to choose some edges. Like here, the drawing on the right shows a case where we chose those edges, this one, also those, and so on, so that the cells between black edges on the right, they should create a tree. There should be one way to get from any cell to any other cell, and we want to maximize the number of chosen blocked passages for among those given in the input. So each of those is something that would give us +1 to the answer if we use it. If possible, we should use all of them. We should maximize the number of those used things. Okay, what happens? Let's instead think about those passages, those sides between two consecutive cells that we will not block. Here I will say that this is something that is not blocked, this is something that is not blocked, and so on. Maybe blue will be better to make a different color, and I will increase the size. This is a tree, and every edge connects two cells, and it either goes through that side that is given in the input as precious side or not. So we can say that every edge has a cost, 1 or 0. What we can say is that if we have an edge like that, it has a cost of 1. We don't like it because it destroys one of the things that we want to preserve. So we have a graph where this edge has cost 0. This is also 0, 0, 0, 0, here 1, here 1, and so on. So we create a graph like this. Every edge, if it passes through the precious side, the one that we want to leave, it has cost 1. We don't want to use it in our tree, spanning tree, and we are looking for MST, the minimum spanning tree in this graph. What trivially gives us solution in complexity O of the size of the grid, h times w, the height times width, times log of something, like depending on your MST implementation, it's something else, I guess. And we can easily get rid of log, just like in, say, Dijkstra. If we have just zeros and ones, then Dijkstra isn't necessary. We don't need priority queue. Here we want MST with as many edges 0 as possible, and for that so you don't have to we don't have to sort edges first of all in log time, because you can just say that some of them are of cost 0, some of them are cost 1. If you use find and union later, then it's still find and union. But instead, what you can say for the given grid, what we will do. First, we can run BFS from every cell, or DFS, and find some spanning tree of every connected component. and we say those are in our tree. And then we just need to connect them in any way. How to connect them in any way? Also, we can use BFS. For example, from every component, we say that there are some edges to other components, and we need to choose some of them. And we don't need to find any union at all here. It's just then if every connected component is now a vertex, and you have some extra edges, maybe multiple edges between two vertices, you just want a spanning tree here. This is DFS or BFS. DFS is easier. So yeah, there are plenty of ways to solve this problem in H times W. Are there any questions? If we just need to print, I don't remember what we need to print. Do we just print the answer? Yes. If we only say what will be the number of those special edges that we cross, then it will be enough to just count connected components. And then if there are, in this case, there are 4 connected components, 4 blue connected components on the left. So this means we need 3 edges. I mean, 3 times we need to cross one of those precious edges, sides, and this matches. On the right we see optimal solution for the sample test, and we got rid of 3 things. Those are the 3 extra edges that we used to connect the blue connected components on the left.